Hi everyone, hope you're all well. The second at-home lab is called Geometric Optics. Geometric Optics is mostly used in imaging theory, the use of things like glass lenses to create images. First of all, let me show you how you can make an image with a simple glass lens. Let me do that first. So I've turned off the lights in the room, and here is my clipboard with paper on it. Here's a glass lens, and I've got the door open to the back to the storeroom of the physics lab, and hopefully you can see I'm making an image. I'm just holding this glass lens in front of this sheet of paper, and it's making an image of what's inside that room. The door, the open door, it's upside down and backwards, so you can see the lights on the ceiling, which looks like it's on the floor here. But that's all it takes to make an image. So it's all you need is a glass lens, something with spherical surfaces like this, and a piece of paper, and then you can make an image. Most glass lenses have spherical surfaces. That is, each of these surfaces is a section of a sphere. You can imagine this is like part of a great big sphere that somebody has chipped this off of. So this has two spherical surfaces. A spherical surface is actually the easiest shaped surface to grind in a solid object. So people have been making lenses for thousands of years, and so they've known about the idea of imaging for thousands of years. But of course today we have a more sophisticated theory of how it works. And now of course we know that light is a wave phenomenon, but geometric optics treats it as rays, so like the paths of individual photons, both of which are legitimate ways to think about it. Last time we talked about refraction, so let me just remind you. So here's a laser beam, and you can see how the laser beam has its path changed by refraction, right? This is just an acrylic block. For some reason you can't see the whole beam there, but in imaging, so here's an acrylic block that's like the cross-section of a lens. And you can see that because of the spherical shape, refraction causes the imaging to be focused to a point. You can imagine the focal point out there where all these parallel rays pass through. So how does focusing allow for imaging to occur? Well, here's my cross-section of my lens. If, let's say, I have a ray coming in here parallel to what's called the optic axis, and this one's also coming parallel to the optic axis, they will all converge. Here's the optic axis, the axis of the lens. These will all converge to a point on the axis when they come through here. But rays coming from a different angle, like say here, will come to a point, will come to a different point on basically that same plane. It's not exactly the same plane, but there will be multiple rays coming from different directions will focus at different points on this plane. And if there's an object out there, let me just get rid of all this mess and say there's an object out there, like a tree. This ray will come in here, focus to that point, or rays coming from this part of the tree. And imagine if I did that for every point on there, thousands of rays, forms an image like that. So there's just millions of rays. From every point on here, there's loads of rays, and there's a very large number of points. So an image is created over here. This is the way our eye works. In the human eye, there's a lens in the front. It's not made of glass, it's made of some proteinous material. But here's a tree out here. An image forms on the inside back of the eyeball where there's photosensitive nerves called retina, and that is how the image is made. And it's similar to the way a camera works. Here's a camera, glass lens. Normally there's a door shut here, the shutter, that doesn't let any light in. And here there's photosensitive film. I'll talk about the old film cameras first. Then the door is open for a fraction of a second, or you can vary the amount of time, and it forms an image. The lens forms an image on this piece of plastic, and then the door is shut again, so it's in complete darkness again. Then you advance the film to the next frame, you take a different picture with, and then you have this processed at the drugstore, and you get photographic plates. A modern camera, like in your telephone, doesn't have a piece of photographic film. It has an electronic device that is light sensitive. It's divided up into many, many pixels, each of which are individually light sensitive. And if there's an object out here like a tree, if there's enough pixels, it'll form a definable image, because each of those pixels records, one little bit of the image of the tree. In other words, it's one point where rays are coming from on the tree, and forms an image, and that's stored magnetically on your phone like that. So all these things are basically the same, the way they form images. There's a subset of the rays coming from an object that are called the principal rays, and it's these principal rays that you can use to determine where the image is actually going to form. Let me show you that. So here's a glass lens. Here's the optic axis. And we can talk about two focal points, the two focal points of this lens. So if rays were coming in parallel to the optic axis from this direction, they would go to this focal point. If rays were coming in parallel to the optic axis from this direction, they would go through that focal point. So a lens has two different focal points. So let me put an object out here. Here's my tree. I'm going to draw what's called the principal rays. This one comes from, it's parallel to the optic axis, gets to the lens and goes through that focal point, right? This one goes directly through the center of the lens where it isn't refracted because of the fact that the surfaces are parallel there. And then this one goes through the near focal point and then over there. You see the three of them converge like that. I managed to make them converge on this drawing. So this is where the top of the tree will be imaged, and the image will be like that over there. So that tells you the distance from the lens where that image will form. If I drew this further away, the image would form at a slightly different place. Now the focal length of a lens is the distance from a focal point to the center of the lens, and the two focal points on either side are the same distance. That distance, this distance, is called the focal length. I just want to tell you one other thing that you're going to do in the lab exercise is determine the focal length measuring some other distances. This distance from the object to the center of the lens, that's called the object distance, d sub O, and this distance from the center of the lens to the image is called the image distance, d sub I. And there's a relationship between the focal length, the object distance, and the image distance. And that's the relationship. On this diagram, of course, I could easily measure the focal length, right? But for a real lens, the focal length is a point out in space in front of the lens. How do you measure that? Well, you can make an image with an object, measure the object distance, the image distance, and then solve this for f, the focal length. Okay, I think that should get you started on the lab.